Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this course on advanced transition metal organometallic chemistry. In the context of our discussion on a variety of palladium mediated CC coupling as well as cross coupling reaction, we have covered allylic alkylation, Suzuki coupling, Hake coupling, Stille coupling, and moving further on we are going to take up another interesting coupling, which is Sonogashira coupling, followed by hydrocyanation reaction in today's lecture. Now, in our earlier lecture we had observed that various palladium mediated cross coupling reaction follow similar catalytic cycle consisting of elementary steps like oxidative addition, transmetallation, cis trans isomerization and reductive elimination. So, immaterial of different cross coupling reaction mediated by palladium, this catalytic cycle containing the above mentioned elementary step sort of remain the same. Now, one of the hallmark of palladium mediated cross coupling or coupling for that matter is the fact that this chemistry is quite stable in under aerobic conditions, that it can be performed in presence of air. The exclusion of air, which is so common for many organometallic transformation, is not required for this palladium mediated cross coupling reaction, and hence this is what make this palladium mediated reaction so popular among chemists in general. Now, another aspect of this cross coupling reaction is of course the high selectivity, the low toxicity, and also functional group tolerance, broad substrate scope, and lastly palladium is not immensely expensive as compared when compared to other magic metals of catalysis like rhodium, iridium and platinum. Now, with a similar story unfolds in case of Sonogashira coupling too. Sonogashira coupling, a sort of more air sensitive coupling of copper acetylides with aromatic halides or electrophiles, which is popularly called as Stephens-Castro coupling and requires aerobic conditions. So, Sonogashira coupling sort of removes the challenges of that reaction and helps the reaction proceed under mild aerobic conditions. So, this is in another way Sonogashira coupling can be seen as a revised version of a very air and moisture sensitive Stephens-Castro coupling of copper organelles and organic electrophiles under mild conditions. So, in short, one can say that Sonogashira reaction provides an alternative pathway to Stephens-Castro coupling of organic copper organelles and organic electrophiles by being able to perform the reaction under mild conditions. Between copper alkynyls and organic electrophiles. So, alternative approach, and these are done under mild conditions in presence of mild conditions in presence of palladium 0 and copper 1 species and a base. So, this can be illustrated using this chemical equation as shown over here. PDLN Cu iodide triethylamine is the base at 25 degrees centigrade, really mild condition, which eliminates this salt of protonated triethylamine and give the corresponding alkyne. So, here one sees coupling between these R1X organic electrophile, where R1 is cationic, and then this copper salt of this terminal acetylene, or so where this alkynyl moiety couples with R1 to give R1 C triple bond C R2. So, X can be bromide, iodide, R can be aryl, alkynyl, acyl, aminocarbonyl, and R2 is widely variable, any variation would do. So, what is seen over here, that the Sonogashira coupling really provides a very mild alternative to a very challenging Stephens-Castro coupling of copper organelles with organic electrophiles that require stringent conditions in terms of exclusion of air and moisture. So, from that perspective, Sonogashira coupling is something which has brought the Stephens-Castro coupling out of stringent anaerobic conditions to ambient aerobic conditions, where such useful coupling can be taken place. Now, this as we had discussed earlier is similar to what we had observed for other cross coupling reaction. What we saw that this air and moisture stability of this cross coupling reaction, also its functional group tolerance, is what it makes this palladium mediated cross coupling reaction in general so special and also advantageous to other kind of coupling reactions that involve, let us say, Grignard, lithium or lithium reagents, which require strict exclusion of air and moisture. So, this ability to perform this Sonogashira reaction or coupling reaction under mild condition is what makes these reactions so special and also makes them so popular among organic synthetic chemists. So, let us now take a look at the mechanism or the catalytic cycle of this Sonogashira coupling. As mentioned earlier, that most of the or almost all of the cross coupling reaction follow similar sets of catalytic cycle in the sense that they all have similar elementary steps like oxidative addition, reductive elimination, transmetallation or cis trans isomerization, and that is no different even for Sonogashira coupling. And we are going to sort of take a look at how these reaction catalytic cycle proceed and then compare the same with its most common analog, which is Suzuki coupling or Stille coupling, which also proceeds by similar catalytic cycle. So, to start with, one sees that it may be a palladium 0 initiating species, palladium 0 species of the type PED L2. Now, this is the initiating species, and this palladium 0 species then undergoes oxidative addition of Rx, and this process is called oxidative addition. To give this palladium R PD L L X. This palladium bis L2 R X then reacts with copper acetylide, and the copper acetylide is formed from terminal acetylene in this following sequence of reaction: terminal acetylene plus R dash 3N and copper X. So, this amine now abstracts proton to give Rn3 R dash 3NH plus X minus, and in turn this X is also abstracted, and in turn copper becomes cationic, and then this acetylide stabilizes on copper to give copper acetylide species, which then goes and attacks this palladium Bsar species and replaces this X to give copper X, and one forms PD R dash L L, and this undergoes cis trans cis isomerization to give the corresponding cis isomer PD L L R, and that under reductive elimination to give the corresponding acetylene or cross coupled product. Now, this step is this reductive elimination step, and this one is this transmetallation step. So, what we see is that this is kind of similar to what has been observed in case of Suzuki and Stille coupling, and that it has the 4 elementary step 1, 2, 3, 4, and that gives the finally cross coupled product. Apart from palladium, which undergoes the catalytic cycle in a palladium 2 palladium 0 couple, copper, there is another additional couple which involves copper copper X going to copper acetylide, and this also undergoes the coupling in terms of the transmetallation. However, the oxidation state of the copper does not change, it stays as copper 1 all the way. In one time it is copper acetylide and another time it is copper halide, and this just goes on in a cyclic fashion as the terminal acetylene get consumed by the base. So, this is a nice catalytic cycle, and this also resembles the other 2 catalytic cycles that we have discussed, like the Stille coupling and like that of the Suzuki coupling, and the cyclical pathway is almost same in the Sonogashira coupling as well. Now, having said that, Sonogashira coupling can be used for a lot of purposes in organic synthesis, and they are used for making natural products like antibiotics, wherever there is a possibility of having Ene-Yne ligand scaffolds, Ene-Yne scaffold. So, to illustrate this, that applications of Sonogashira coupling coupling application in synthesis of antibiotics. Now, this is nicely illustrated by the reaction given over here, C5 8 11 OH Cl plus TMS acetylene is in presence of MECN whole to PdCl2 THF, copper iodide and piperidine at room temperature, giving OH C5 H11 TMS. So, this is a nice example where this Ene-Yne this is Ene, this is Yne, this Ene-Yne framework is constructed right by coupling between an alkene and the acetylene. So, it is one of the advantage of beautiful approach of the Sonogashira coupling is that it involves a direct splitting or direct stitching of acetylene with that of an olefinic halide, so that this Ene-Yne framework can be conveniently synthesized, and the convenience of this synthesis can be gauged from the yield of this reaction, which is extremely high, about 97%. So, what this underscores is the fact that Sonogashira reaction provides a very smooth direct approach to these Ene-Yne frameworks, and that is successfully used in synthesizing many natural products, and the one that is discussed over here that could be synthesized very efficiently 97% yield, as is shown over here. Now, the scope of this Sonogashira coupling is not limited to just forming conveniently the Ene-Yne framework, but also its carbonylative variant is also known. By that I am going to illustrate this with a beautiful example. So, carbonylative variant of Sonogashira coupling is also known and this beautiful example involves performing Sonogashira coupling in presence of carbon monoxide and have been used in the synthesis of pyridone, as is shown over here. So, orthoiodoaniline with phenylacetylene in presence of DPPF PdCl2 under CO at high pressure 20 bar pressure in presence of diethylamine at 120 degrees centigrade give this bicyclic compound pyridone in 70% yield. Now, this reaction consists of two parts. The first one is the carbonylative coupling, and the second part obviously first is the carbonylative coupling to form this CO acetylide moiety, and then obviously the next part is this cyclization intramolecular cyclization that proceed in tandem fashion. So, what one sees is a beautiful example in which one can extend the scope of the Sonogashira reaction in terms of providing the carbonylative variant carbonylative coupling of Sonogashira reaction, followed by intramolecular cyclization to produce this pyridone in 70% yield. So, one of the hallmark of Sonogashira reaction can be seen from this utility, and that these can be extended to produce bicyclic compounds that involves tandem reactions. Not only this Sonogashira coupling, it is also a special kind of Sonogashira coupling as performed in presence of carbon monoxide at high pressure. It gives carbonylative coupling followed by intramolecular cyclization to produce this pyridone bicyclic compound in a tandem fashion in high yields, 70% yield. So, with this I would like to conclude today's discussion on Sonogashira reaction. As mentioned in the beginning of the talk, that we have been discussing Sonogashira reaction in the context of palladium mediated CC cross coupling reaction, particularly with regard to the other more popular cross coupling reaction like Suzuki reaction, Stille reaction that had been discussed in the earlier context. So, what we see is a similar story unfolding in case of Sonogashira reaction too. Obviously, Sonogashira reaction along the same lines provides a more convenient direct approach for constructing Ene-Yne double bond and Yne framework can also under mild conditions, and which have been used for making various scaffolds of natural products which are in great demand in the world of organic synthesis. And also we have seen that this coupling mechanism for Sonogashira coupling resembles very much what we had observed for Suzuki and Stille coupling, that it has 4 elementary steps. They involve oxidative addition, transmetallation, cis-trans isomerization and reductive elimination. Also, there is another interesting thing is, apart from palladium which is required for the palladium mediated cross coupling reaction, there is also another second metal involved, which is copper 1, and this copper 1 is also present in a catalytic fashion as it does a couple between copper halide and the copper acetylide moiety. We have also seen the scope of the Sonogashira coupling can be extended to carbonylative coupling and followed by intramolecular cyclization that gives this bicyclic compound. So, a beautiful scope for chemistry is represented in form of Sonogashira coupling and the corresponding applications of such coupling that we have discussed. So, with this I would like to conclude today's discussion on Sonogashira coupling, and we are going to take up another interesting topic of hydrocyanation reaction in the next lecture in this overall topic of CC bond forming reaction. I thank you again for patiently listening to today's lecture, and I look forward to being with you in the next lecture when we take up this new topic of hydrocyanation reaction as a part of CC bond forming reaction. Till then, goodbye and thank you.